Hello, welcome to this lesson of the Linear Algebra Tutor. We've covered a lot of material so far. Most recently, we've been talking about solving systems of equations. We've figured out that we can have consistent systems which have a single unique solution for the set of equations. We can have inconsistent systems which don't have any solution at all for that system. And then we can have dependent systems, which means there's an infinite variety of points that can satisfy the set of equations. So we've built our skills up, and we've been using row reduction techniques to do that, and you're kind of, at this point, starting to understand why matrices are really useful little animals. Now what we're going to do is we're going to start to continue working with systems of equations, but we're going to talk about what we call homogeneous systems of equations. Homogeneous systems of equations. Now those of you who have taken differential equations in the past, which may or may not be some of you guys, but whoever has, you're going to start to see a little bit of similarity in what we're talking about here in relation to what you may have learned in a differential equations class. You certainly don't need to know any differential equations to understand this, but I'm just saying if you have taken that class, turn that part of your brain on and try to look for some parallels. I'm going to point them out to you as well. You're going to learn some things in here, and we're going to tie it up in a nice bow, hopefully, that will jog your memory in relation to something that you already learned. Okay, the first thing is, what is a homogeneous system of equations? What it means is, instead of having a bunch of equations with numbers on the right-hand side of the equal sign, it means that ax, instead of ax equals b, we just say ax is equal to 0. Homogeneous just means we have a coefficient matrix, then we have a column vector with x, y, z, or whatever we're solving for, but on the right-hand side of the equal sign, there's a 0. There's a 0. You might say, why do we care about that? It turns out that homogeneous systems of equations are very, very common in nature. When you build a system like an electric circuit, or if you build a spring system or whatever, then the homogeneous version of the equation that describes the system is representing how you built the system. It's representing the components and the connections and such. For a circuit, it might be in relation to the components that you chose to put into the circuit. Now, if you have another set of equations with numbers on the right-hand side, or if you're talking about differential equations where you have functions, maybe cosines or sines on the right-hand side, then you're now driving your system with a forcing function. In other words, you've hooked up a function generator or a voltage source to your circuit, and you're driving it. So the homogeneous version of the equations usually describe the system itself. When you have non-zero numbers here, you've got the whole enchilada, including any driving functions that you're sending into your system. So kind of keep that in mind. I'm going to come back to that a little bit later. So when we have a homogeneous system like that, there's really only two possible ways you can solve it. The most simplest, trivial case is if all of the variables that you care about, x, y, z, in this case we'll call it capital X, if they're equal to 0. This is a solution to this equation when you think about it. If you have ax is equal to 0, a valid solution would be that x is equal to 0. But don't forget that this is not an equation from Algebra 1. This is a matrix equation. So A is a coefficient matrix, x represents 2 or 3 variables, maybe more, and what's on the right is usually numbers in this particular case, all right? So if we say x is equal to 0, what I'm saying is I have a system of equations. They're equal to 0. So I could say x is equal to 0, y is equal to 0, z is equal to 0. If I set all of those equal to 0, then by definition, this equation will be satisfied. Unfortunately, that's not a very interesting solution. Who gives a you-know-what if all of your variables are 0? That's not a real solution. I mean, it's valid, but it's not interesting. So if the only solution to this set of equations is if you set your variables equal to 0, that's called a trivial solution. It's trivial because it's kind of pointless. If I get a set of equations and I say, oh yeah, I can solve that, I'll just set all my variables equal to 0, then that's kind of like not very useful. But if you get an answer such that the variables x, y, z, whatever you're solving for is not equal to 0, that's called non-trivial. Non-trivial solution. And in many cases you can find a set of variables, even though you've got it set equal to 0 over here, you can find a set of values that go into your variables that will make that guy satisfied, that will solve that set of equations. It's called non-trivial. I'm telling you these definitions because on your test, your teacher or whatever might say, does this set of equations have a trivial solution or not? And you'll need to know what does trivial mean, right? And so you'll have to know those definitions. So what I'd like to do at this point is draw a line under here, and I'm going to write a set of equations down on the left. I'm going to write another set of equations down on the right. Now first, I'm going to write down the non-homogeneous version, which is AX is equal to B. This is what we've been doing so far. All right? So let me write that down as follows. I'm going to try not to cramp it up too much. I'm trying to put that over here and then something else over here because I want to draw a direct parallel between the two. So if I have a set of equations, X plus Y minus Z minus W is equal to 1. This is 4 variables, X, Y, Z, W. The next equation would be 2X plus 2Y plus 2Z minus 2W is equal to 6. The third equation is 3X plus 3Y plus Z minus 3W is equal to 7. And the fourth equation is X plus Y plus 3Z minus W is equal to 5. So this is what we call the homogeneous set of equations. Non-homogeneous, because there are numbers on the right-hand side of the equal sign. Now what I'm going to do is draw like a little divider here. And now over here we're going to write the homogeneous version. And that's AX is equal to 0. So basically it's exactly the same set of equations, but I'm going to put 0 on the right-hand side. And I'm doing this for a very specific purpose. I'm doing it so that we can draw some conclusions here. So this set of equations would be X plus Y minus Z minus W is equal to 0. Notice it's the same equation, but I just, instead of a 1, I put a 0 over here. 2X plus 2Y plus 2Z minus 2W is equal to 0. Same exact equation here. Now I have 3X plus 3Y plus Z minus 3W is equal to 0. And then I have X plus Y plus 3Z minus W is equal to 0. So basically, these are the same set of equations. The coefficient matrix over here is the same as the coefficient matrix here, but the matrix on the right-hand side of the equal sign here is non-zero. The matrix on the other side of the equal sign here is 0. So when you have everything on the right-hand side of the equal sign for all of your equations equal to 0, that's called a homogeneous set of equations. All right? So how would we solve this? Let's not get too fancy. How would we actually solve it? Well, we would write an augmented matrix, right? We would come in here and we would write down a matrix, and the matrix would look like this. 1, 1, negative 1, negative 1, 1. And then here we'd have 2, 2, 2, negative 2, 6. And then we'd have 3, 3, 1, negative 3, 7, 1, 1, 3, negative 1, 5. This would be the augmented set of equations, equation matrix. Let me just make sure I didn't write anything wrong as I go down here and just kind of check myself. Now over here, the coefficient matrix is exactly the same. The only thing that's really different is that there's zeros on the right-hand side. So what I would have for this would be very similar. 1, 1, negative 1, negative 1, 0. And here I would have 2, 2, 2, negative 2, 0. 3, 3, 1, negative 3, 0. 1, 1, 3, negative 1, 0. I know your eyes are probably crossing now and you're like, why is he doing all of this? But I promise you that at the end of the day, we're going to solve both of these and we're going to find something really interesting about the solution and how the solution of the homogeneous set of equations relates to the solution of the non-homogeneous set of equations. Because they're exactly the same thing, except I have numbers in this case and I have zeros over here. All right, now I'm not going to do row reduction on these because we've done row reduction enough. I think you have enough practice with that. So I'm going to draw a little arrow and it's going to say row reduction. This does not mean railroad. This means row reduction. And over here, we're going to do some row reduction as well. Now on the left-hand side, what we actually get when we do the row reduction is we get 1, 1, 0, negative 1, 2. And here we get 0, 0, 1, 0, 1. And then, interestingly, we get all zeros here, and we get all zeros here. Now this should instantly tell you that there's going to be an infinite set of solutions for this set of equations anyway, because I've got all zeros here and all zeros here for not one, but two of the variables. That's a huge clue, like we've already discussed, that there's going to be an infinite set of solutions here. Let's see what we get if we were to do row reduction on this side. What we get here is, not surprisingly, 1, 1, 0, negative 1, 0, 2, whoops, of course there's not a 2 there. We get 0, 0, 1, 0, and then we get 0, 0, 0, 0, and we get 0, 0, 0, 0, 0. So do you see how these are similar? The coefficient matrix, once we do all of the row reduction to get from here to here, it ends up in exactly the same place as on this set of equations, because when we do row reduction, all we're trying to do is get a diagonal matrix on the left-hand side. So exactly the same steps occur to get from here to here as we do to get from here to here. So on the left-hand side, the matrix matches exactly what we get for the non-homogeneous case. There are numbers here where in fact there are zeros here, and that kind of makes sense from the way we have it set up as well. So again, you might be thinking at this point, why are we spending so much time talking about this? What I would like to do is let's go ahead and write a solution for the non-homogeneous set of equations. That's this set of equations right here. Let's write a solution down. All right, we're going to get the answer, we'll circle it, and let's write the solution down for the homogeneous version of the equations using this, and write that down. And what you're going to find is that there's a strong similarity between the two. So we're kind of getting practice with two things. Number one, I'm introducing the concept of a homogeneous system of equations to you and showing you how to solve it. But I'm also going to draw a parallel to the non-homogeneous set of equations, and there's going to be an important kind of theorem that pops out at the end when we do this comparison. It's a lot more fun to do it this way than just write the theorem down, tell you, and you're like, that's not very useful. But when you see it, you'll understand. So I don't want to write this matrix down again. So we have 1, 1, 0, negative 1, 2. So if we're solving the non-homogeneous version, I'm going to write down non-homogeneous. That's what we're solving right now. We're putting the other thing on the back burner from now. The top equation is x plus y, there's no z here, minus w is equal to 2. So it's x plus y minus w is equal to 2. The next guy, this is x, y, z, so this is z. Z is equal to 1. All right. Now, if this equation was kind of left alone and it represents some information about x, y, and w, and this equation was manipulated such that with a row reduction such that it gives you information about z, then even though this is all about zeros and this is all about zeros, we're going to say that this third equation gives us information about y, the second variable, and this equation gives us information about w, the fourth variable. What I'm trying to say is 0 times y is equal to 0, and 0 times w is equal to 0. All right, make sure you understand that. It's a little bit hard to see because I skipped the row reduction steps, but basically the bottom line is when I did the row reduction, I didn't really move this line around at all. So you can say that this top line gives us information about our variable x, our first column. The 1 here gives us information about z. So the only other two variables we have are y and w. So we're saying 0 times y gives us 0. 0 times w gives us 0. So we're trying to translate what the matrix has into actual equations we can write down. That's the way that we proceed and write our infinite set down. So notice now that you can put any number in for y and satisfy this, and you can put any number in for w and satisfy this. So what this basically says, or what these two pieces of information say, is that y is equal to k1, we'll call it k1, and w is equal to k2. You can call them anything you want, but basically they're two different constants, k1, k2, two different constants. Once I know k1 and k2, I can find corresponding values of the other variables very, very simply. So what we're going to do is go back here and we'll say, first equation, draw a little line here, x is equal to 2 minus y plus w. I just move the y over, move the w over. But now I know that y is equal to k1 and w is equal to k2. So this is important. I'm going to circle this. Okay. And then I'm going to go under here So that's for the variable x. The variable y we know is just equal to the constant k1. So that's important. I'll circle that. Z is already given to us as an answer on the board. It's a fixed value. Z is equal to 1. So that's important. There's nothing else to do there. And then for the last thing, w, the last variable, w is equal to k2. I'll circle that one. So now I have a relation for x, a relation for y, a relation for z, and a relation for w. And now I can write everything down. So then what I'll say is my solution vector, my solution column matrix x, is equal to, remember first we go down x, y, z, w and look for numbers. X has a number 2. Y doesn't have a number, just has a k, so we put a 0 there. Z does have a number, so we put a 1 here. And w doesn't have a number, it just has a k, so we put a 0 here. This follows from what we did last time. Plus k1. Are there any k1s in the x? There is, -1 times k1, so we put -1. Are there any k1s for y? Yes, there is. We put +1 there. Are there any k1s for z? No, there are not, so we put a 0. Are there any k1s for w? No, there are not, so we put a 0 here. And then we add to it k2 and open up another column matrix, a column vector. Are there any k2s for x? Yes, there is, just one of them. Are there any k2s for y? No, there's not. Are there any k2s for z? No, there's not. Are there any k2s for w? Yes, there is. All right, so this is the solution of this set of equations. It is a dependent solution, but now it's a little more interesting because it's not just dependent on one constant, it's dependent on any two constants. The reason it's dependent, you have freedom of those two constants to choose to lay down your solution, comes directly from the matrix. There were 2 rows of that matrix that had all zeros. That means 2 of the variables are free to be anything you want. The other variables will be locked down as a result. So if I pick a value of k1 is equal to 1 and k2 is equal to 5, or whatever I want to choose, then I'll just say that x would be 2 plus k times this plus k times this. That's the value of x. The value of y is going to be 0 plus k times 1 plus k times 0, and so on. So you read it off in terms of rows. X, y, z, w. And that is the answer. So it's a dependent solution, dependent on 2 values, k1, k2. Now, what we have done up to this point is we have solved the non-homogeneous version, and we got a column vector, a column matrix, whatever you want to call it, of numbers. And we had a linear combination of 2 other column vectors that depend on arbitrary constants. I want you to remember that. I want you to put it in the back of your mind, because what we're going to do now is kind of put that to the side. Let's solve the homogeneous version right here. Notice that the left-hand side of the matrix, 1, 1, 0, -1, all this is the same as this. The only difference is we have zeros here. So let me go to another board and let me write down what we get when we take a look at the homogeneous version. Okay? Now I don't need to really slide back there because remember the coefficient matrix was the same, so it's going to be x plus y minus w, but it's going to be equal to 0. That was the first row in that matrix. The second one is z is equal to 0, right? It's exactly the same as what we got here. Z is instead of equaling 1, it's equaling 0. Z is equal to 0. And then we have all zeros for the other 2 guys, which in an analogous fashion to what we had before, 0 times y is equal to 0, 0 times w is equal to 0. So you go through exactly the same exercise. These 2 guys mean that y is equal to k1 and w is equal to k2. This means that z is locked down at a value of 0. There's nothing infinite about this. Z is just 0. All right? So then we go and solve this top equation. X is equal to -y plus w, which is equal to -k1 plus k2. Y is equal to k1, which we get from here. Z is equal to 0. W is equal to k2. I like to write it in terms of x, y, z, w, because now I'm going to write it in terms of this matrix representation. The answer is going to be, let's first find our numbers. There's no number here. there's no number here, there's no number here, there's no number here. So there's really no sense in writing down numbers there. So we look for linear combinations of K1. Is there a K1 here? -1 for here. Is there a K1 here? 1 goes there. Is there a K1 there? No. Is there a K1 there? No. So we put 0, 0. And then we say K2. Is there a K2 here? Yes, there is. Is there a K2 there? No, there's not. Is there a K2 there? Of course, there's not. Is there a K2 there? Yes, there is. All right, so you see that this guy is the solution to the set of equations, but when you take the right-hand side of the system and put all zeros there. And what you get is K1 times this column matrix, K2 times this column matrix. Now I want you to remember what these look like. -1, 1, 0, 0, 1, 0, 0, 1. Move over here. For the non-homogeneous, it's K1, -1, 1, 0, 0, 1, 0, 0, 1. The only difference between the non-homogeneous version and the homogeneous version is the fact that for the non-homogeneous version, we have an extra column vector there. So the way that you want to, the conclusion I want to draw here is I want to call this, instead of just calling it x, I want to call it x sub h, meaning this is the solution to the homogeneous version of the equations. When I given a system of equations, if I take everything off the right-hand side and put zeros there, I'm solving the homogeneous version. So the answer I get, I'm going to call it x sub h, okay? And then I'm going to call this column vector, just this column vector, I'm going to call it x naught, okay? And then what you can say is that the solution for any non-homogeneous set of equations is equal to some column vector, x naught, plus some solution to the related homogeneous set of equations. So this we're going to call a particular solution, and this we're going to call the homogeneous solution. This should ring a bell to anybody watching this that has seen or taken a class in differential equations. If you remember, differential equations are much, much harder to solve than these things. But still, a common solution technique to differential equations, if we're given a very complicated set of differential equations, is we'll take everything on the right-hand side of the equal sign and we'll set it equal to 0. That is basically giving us the related homogeneous form of the equations. And then we solve that. We get the answer. We call that the homogeneous solution. Then we have other techniques to go find the particular solution, and the kind of a fundamental theorem of differential equations is also a fundamental theorem of linear algebra, is that you can do this for linear algebra as well, is that the solution to any old set of system of equations is a sum of what we call a particular solution and the solution of the related homogeneous differential equations. So this is an important theorem that you'll see in almost every linear algebra class when you study systems of equations. The solution to a set of equations is always the sum of what we call a particular solution. By the way, why is it called a particular solution? It's because this column vector arises from the particular numbers that we have on the right-hand side of this equation. So remember I kind of told you before, I kind of hinted, I said, all right, if we build a system, if we build a circuit or something, we choose components, right? We don't drive it with anything, we don't turn any sources on, but we just build the system, all right? Then you can kind of think of this homogeneous set of equations as describing what the system is doing. And then you can also kind of see, like if you want to hook a function generator up to the circuit, right? Then you can kind of think of these numbers on the right-hand side as being the forcing functions into my system, right? Then it kind of makes sense that the total solution to how this thing's going to behave is going to be somewhat related to the sources that I hook up. That's the particular solution, right, that we just talked about. It's also going to relate to how we built the system, which is what we call the solution to the homogeneous form of the equations. The solution because of the way we built the system with those particular values of resistors and capacitors and things like that. And that is what we're trying to say here. The solution to a set of equations in general is a particular solution plus whatever we get as a solution to a set of homogeneous equations. So this is a fundamental theorem that you're going to come in contact with in linear algebra. I don't plan to do any more problems, what I could have done is I could have just given you this and said, hey guys, this is true. But I wanted to walk through it with you and show you that, hey, the difference between non-homogeneous and homogeneous is just the numbers on the right-hand side. Here's the matrix that you would get. You do row reduction, you're going to get this here and this here. These coefficient matrices will be the same. The only difference will be what you get on the right-hand side. So when you solve the non-homogeneous case, you're going to get this. When you solve the non-homogeneous case. When you solve the non-homogeneous case, you're going to get this. When you solve the homogeneous case, you're going to get all of the infinite part going on there, right? And so then you can learn to identify solutions as a sum of a particular solution, particular to the numbers that were on the right-hand side of the equal sign, plus the infinite part that comes about from the related homogeneous form of those equations. All right, that's about all I have to say about it. I'm trying to draw some parallels to things you may have studied in the past. So I hope you've enjoyed that. We've taken a very, very long road with solving systems of equations in terms of using linear algebra and row reduction. Follow me on to the next lesson. We're going to begin to talk about inverse of matrices, which are also extremely important in all topics in linear algebra.